Hello everyone and welcome. In this video I will introduce the first chapter of the Mathematical Analysis 2 course. The title of this chapter is Limited Development. This presentation covers the following key points. First, we will explain what the limited polynomial developments means. Second, we will study the Taylor's formula. Third, we will explore the properties of the limited developments. Fourth, we will look at the limited development of usual functions. Finally, we will see the operations on the limited developments. Let's get started with introduction. The limited development is useful in many areas of mathematics and physics, including solving differential equations, performing integrations, evaluating limits and analyzing local behavior of a function and its polynomial approximation. Let's now introduce the definition of limited development. Let f be a real function defined on an interval I, and let x0 is in this interval, and n belongs to the set of natural numbers. We say that f admits a limited development of order n at the point x0 if there exist real numbers a0, a1 to an such that as x tends to x0, the function f of x can be written as the following formula. The last term of this formula represents the remainder. Example, let's consider the function f of x equal 1 over 1 minus x. First, recall the identity 1 minus x to the power of n plus 1 equal 1 minus x times 1 plus x plus 2x to the power of n. Using this identity, we can write the following equality. This means that the function f admits a limited development of order n at 0. Let's now define Taylor's formula. Let x0 be any real number and let f be a function that is differentiable at least n times at the point x0. Then the Taylor formula of order n about the point x0 is the following formula, where the small l term is called the Young remainder and it becomes negligible as x tends to x0. Remark: if x0 equals 0, Taylor formula with Young remainder is known as Maclaurin's formula. Let's look at an example. We want to find the Taylor formula of the exponential function of order 3 at the point 0. From the table of derivatives, we see that all the derivatives of exponential x at 0 are equal to 1. So, using the Taylor formula of order 3, we get f of x equal 1 plus x squared over 2 plus x cubed over 6 plus O of x cubed. Let's move on to the next remark. The Taylor-Young formula of a function f of order n at the point x0 is the limited development of order n at x0. In this case, The coefficient an is given by an equal the north derivative of f of x0 over n factorial. So, the limit development of order n at x0 of f is given by Taylor-Young formula of order n if f is differentiable at least n times at the point x0. We will now study the main properties of the limited development. One important property is the following. If a function f admits a limited development of order n at the point x0, then the limit of f of x as x approaches x0 exists, is finite, and is equal to a0. This criterion is often used to prove that a function does not admit a limited development at x0, especially when the limit does not exist or not finite. As an example, the function logarithm of x does not admit a limited development of order n at 0 because its limit as x approaches 0 is minus infinity, so the limit does not finite. Here we show some very famous limited developments of common functions of order n at 0 using Maclaurin's formula. Operations on limited developments. Let's start with the sum. If the function f admits a limited development of order n at 0, and the function g also admits a limited development at 0 of the same order, then the sum f plus g also admits a limited development at 0 of order n, which is given by the sum of the two limited developments. Let's look at an example of the sum of two limited developments. Now let's talk about the product of two limited developments. If two functions f and g both admit limited development of order n at 0, then f times g also admit limited development of order n at 0, obtaining by keeping only the monomial of degree n or less in the following product. This is an example to explain. Thank you for watching this video.